Hello, mathophiles. Welcome to the first of two videos on what's called the mean value theorem, which is an important result in calculus that is used in turn to prove other, possibly even more important results in calculus. This first video will serve as an introduction and a statement of the theorem, and will then work out an example of the type of problem that often is asked on exams. And then the second video will involve a look at what happens when the assumptions of the theorem are not met and why the conclusion might then not follow. As you can see, at the left endpoint of that interval, we're at the point -540. At the right endpoint, we're at the point 4, -14. And a little algebra 1 will show you that the slope of that secant line that you see on the screen is -6. So we're going to start by looking at tangent lines to this curve. So there is a movable point, and it, depending on its location, describes any one of many multiple tangent lines to the secant line that you see here. If you drag it around a little bit, you'll find that there may be times when the tangent line is parallel to this secant line. And what that would mean is that you found a point on the graph of the function where the tangent line, being perpendicular to the secant line, shows that the instantaneous rate of change at that point is equal to the average rate of change over that entire interval. And this appears actually in this case to happen twice. One down here at about 1.6 or so, x equals 1.6, and another up here in the neighborhood of x equals -3.6, 3.7, something like that. All right. So it is at least conceivable that you can find yourself in a situation where there are tangent lines on an interval that are parallel to secant lines from one end to the other of the interval. There's another way that we can approach this, and that is to, instead of having a tangent line at various places, drag around a line that is parallel to the secant line. So here is, grabbed the wrong slide. So here is a line that also has a slope of -6, which makes it parallel to the secant line. And as you can see, unsurprisingly, given what we just did with those tangent lines that we were moving around, we find that at the same two locations, we see that this draggable parallel intersects the curve at those points. So you can approach it from the point of view of tangents and, oh, look, they're parallel, or you can approach it from the point of view of parallels, oh, look, they're tangent. Now, why should this be? Informally, if you think about it, function has to get from -540 to 4, -14, and either it goes there in a straight line, which of course it doesn't being a cubic, or it spends some time getting there faster, if you will, at a greater rate of change, and sometime getting there at a lesser rate of change. And if it starts out faster, in order to get to where it's going, it has to at some point get slower. And in the transition from faster to slower, or in terms of the tangent line slope, and the transition from steeper to shallower, it's got to also be equal. It's got to pass through that value. A formal proof of that is beyond the scope of this video, but that is the essence of the logic of the proof. We're next going to look at a statement of the mean value theorem, and then we're going to work through an example of the kind that one typically sees. First, a statement of the theorem. If f is continuous on closed AB and differentiable on the corresponding open AB, then there has to exist at least one C in open AB, such that f prime of C is equal to f of B minus f of A all over B minus A. And of course, f prime of C is the slope of the tangent line at that location, and f of B minus f of A all over B minus A is the slope of the secant line. So it says they've got to be equal. There is a special case of the mean value theorem that sometimes gets mentioned separately for historical reasons because I believe it was discovered first, and that's what's called Rolle's theorem. And Rolle's theorem just adds the additional requirement that f of A and f of B be 0. And so that ends up meaning that the slope of the secant line is 0. And so the conclusion then becomes there must be some value of C in open AB such that f prime of C is equal to 0. So it's just a special case of the mean value theorem, but you sometimes hear it referred to as a separate thing. Here is our sample problem. And again, f of x is x cubed plus 3x squared minus 24x minus 30 enclosed negative 5, 4. And a little arithmetic will show, and I believe we mentioned this, that f of negative 5 is 40, f of 4 is negative 14. So if we draw a secant line from the one point to the other, its slope is going to be, as I believe we said, negative 6. And that's straight up old algebra 2. So, not even that, algebra 1. So, when we say that the instantaneous rate of change and the average rate of change are equal, we're saying basically that the derivative is equal to this value of negative 6. So what is f prime? If this is f, that's going to be 3x squared plus 6x minus 24. And for the derivative to be equal to the slope of the secant line, it must be the case that 3x squared plus 6x minus 24 is equal to negative 6, or 3x squared plus 6x minus 18 is equal to 0. And if you pop this into the quadratic formula, you get that x is negative 1 plus or minus the square root of 7. And these approximate out to about 1.646, or about negative 3.646. And these are in nice accord with the locations that we observed on the screen. This is a very typical type of test problem that gets addressed at the mean value theorem. You're given the function in the interval. You're asked to find the values of x or c, whatever we're calling it, at which the conclusion obtains. And so you take the derivative, you set it equal to the slope of the secant line, you solve for the x or the c or whatever letter of the alphabet you've chosen to use. So that's an introduction and example. Second video, which is forthcoming, will show a couple of instances in which the assumptions of the theorem about differentiability and continuity are not met, and how that causes it to be not necessarily the case that you'll see the outcome. Happy mathing.